So thank you. Okay. Thank you, Mr. Koski. I'm Keigo Matsumoto from the University of Tokyo. This is our demonstration, Unlimited Corridor handrail version. A user walking along semicircle handrails is holding them, but C sees the image of holding straight handrails and walking straight through an HMD. By using this system, we compress an infinite ladder-shaped virtual space into a small real space. So our research motivations are very simple. You'd like to walk through an infinite virtual space within a smaller real space without complicated mechanism. As you know, natural interaction is important for creating compelling virtual reality experiences, and locomotion is one of the most common and universal tasks performed when interacting with virtual environment. So many previous research projects have proposed methods for exploring a huge burst virtual reality space, but many of them use complex mechanisms and cannot be experienced only with commercial available HMDs. So there is one way to solve these problems: redirected walking. As Carlos and Arinant explained already, redirected walking is a methodology for manipulating spatial perception by presenting images that are different from actual movement. And it's based on the fact that vision plays a dominant role in our spatial perception. Using this methodology, we can compress a large virtual environment in a small physical space with maintaining a sense of natural walking. So redirected walking techniques can be classified into subtle and overt techniques. Subtle techniques, such as curvature gain, can manipulate users' position and orientation without noticing them when the magnitude of the manipulation is beneath a certain detection threshold. And overt techniques, such as reorientation, are very effective in changing the user's orientation. However, of course, there are some problems with redirected walking. With subtle techniques, their detection thresholds are usually very severe, so it is often insufficient to compress a huge virtual space. On the other hand, their overt techniques will be easily noticed by users and may cause simulator sickness. To overcome those challenges, we propose Visuo-haptic Redirection. Visuo-haptic Redirection uses visual-haptic interaction for enhancing the redirected walking effect. Visual-haptic interaction is a phenomenon in which perception of size, shape, and position is affected by vision, because vision dominates the integrated visual-haptic perception. For example, Ban et al. Modified the haptic perception of the curvature, angle, and size of a cylindrical object by manipulating visual stimuli. In Visuo-haptic redirection, visual information and modified haptic information by visual-haptic interaction are combined to manipulate spatial perception more effectively than conventional visual-only method. Our previous research project showed that the effect of curvature gain, which is one of the redirected walking techniques, can be improved by using passive haptic stimuli of walls when the radius of curvature of the walking path is 2 meters or less. Based on this result, we created an unlimited corridor wall version, but it was not yet clear whether Visuo-haptic redirection would work under non-wall haptic stimuli or at a different radius. So this time, we created unlimited corridor handrail version. Instead of using walls, handrails were used as passive haptic stimuli. The reason for choosing hand rails for haptic stimulation is that it is the most common object to touch while walking in daily life. The user can see and move her virtual hand, and when she tries to hold the virtual handrails, she will hold the actual handrail. The user is asked to walk the red balloon while holding the handrail. On the way, there is an obstacle, so the user must bypass. Users wear a HTC Vive Pro headset, 2 Vive trackers, and a MSI backpack PC. The trackers were used to tracking users' hands position to present virtual hands. We installed 2 semicircular handrails with a radius of 2.5 meters at an interval of 1.2 meters, and 4 base stations at each corner. The radius of this handrail is much smaller than the 22 meter, 11 meter, and 6.4 meter radii conventionally required for redirection. To mapping the real space and the virtual environment properly, we divided the real space into the inner and outer peripheries. In the inner periphery, we map the position and orientation of a user's head and hand with a one-to-one correspondence to the virtual camera and virtual hands. On the other hand, in the outer periphery, we apply a customized curvature gain to change the position and orientation of user's hand and head. This figure shows the model case of the walking path. Orange paths means real walking paths, blue path means virtual walking path, and a red cross means a virtual obstacle. The users walk about 40 meters from the start point to the goal point. To verify whether Visuo-haptic redirection works with handrails, we conducted a user study. We compared haptic and non-haptic conditions. Under haptic conditions, users walked with holding the handrails, while under non-haptic condition, users walked without holding the handrail. 22 participants conducted our user study. We used questionnaires to measure simulator thickness, presence, and sensation of straightness. As a behavioral indicator, we measured walking speed. The reason why we measure the walking speed is that walking speed could affect the effect of redirection. It has been shown that the effect of redirection increases if users walking slowly. And because of the conventional method cannot evaluate the sensation of straightness directly, we made a new questionnaire. Here is the questionnaires of sensation of straightness. The questionnaire consists of 4 questions, each on a 1 to 7 scale. From our pre-user study, we confirmed that the score of this questionnaire was proportional to the result using conventional methods. This figure shows the walking speed. Error bars indicate the standard errors. Although the users walked relatively slowly, there was no significant differences in walking speed between non-haptic and haptic conditions. Therefore, the walking speed between the 2 conditions is unlikely to have a significant effect on straightness. This figure shows the box plot of sensation of straightness scores. We found a significant differences in sensation of straightness between the non-haptic and haptic conditions. This result suggests that visuo-haptic interaction enhance the effect of the redirected walking technique. And this figure shows the SAS presence questionnaire scores. Under both non-haptic and haptic conditions, the scores were greater than 5. This means the users were immersed into the virtual environment. and there is no significant differences between these conditions. And last, this figure shows a simulated sickness total severe scores. We found a significant difference between the pre and post SSQ scores. This result implies that our system causes slightly simulated sickness, and it may owe to the use of the large curvature gain. From the experimental result, it is thought that the improvement in the sense of straightness was due to haptic stimuli of the handrails, and combined with previous research results, Visuo-haptic redirection worked with haptic stimuli of handrails as well as walls. Therefore, Visuo-haptic redirection is thought to work with various haptic stimuli. Of course, the proposed method has some limitations. First, dedicated walls and handrails are required, and this is not a small cost. Second, the content is subject to certain restrictions, because users have to walk by holding handrails or touching walls. The third is the system can only present a larger shaped virtual space. So, in order to solve these limitations, we are conducting research on method of presenting surrounding environment as haptic cues, and method of applying optimal redirection techniques using machine learning. So this is a summary of our study. Thank you for listening.
Great, thanks, Keigo.